Welcome to Yurix AI. This is Lecture 9 of LLMs from Scratch, Zero to Builder. I am so pumped to have you guys here today. If you've been following along with the series, you know we've been uncovering the real magic behind large language models. Today, we are welcoming all of you US beginners to what I like to call the assembly line of language. We're literally going to take raw text and start mechanically preparing it so that an AI can actually digest and understand it.
Here is our Zero to Builder roadmap, laying out our learning objectives for today. We're going to cover 1. LLM input target pairs, 2. Coding pairs in Python, 3. Understanding context size, 4. Implementing a data loader, 5. Batch size and parallel computing, and finally, 6. Stride and batch effects. We've got a lot of ground to cover, so let's just dive right in.
Kicking things off with Section 1, LLM input target pairs.
Okay, so the absolute standout idea, the core philosophy you really need to remember today, is that LLMs learn simply by predicting the next token. That's it. And to teach them how to do that, we have to slide a window across our text to create very specific pairs of data. So what exactly is an input target pair? Well, in layman's terms, imagine you're reading a sentence, and I just cover up the last word. The words you can actually see, that's your input. And that hidden word you're trying to guess, that is the target. So an input-target pair is really just a sequence of tokens, which, remember, are just text chunks converted into numbers, paired with the exact next token in that text. Our model's entire job is to look at the input and figure out how to accurately predict that target.
When you actually visualize this, it's beautifully simple. Let's say we have our input sequence, which we'll call X. It contains the tokens 1, 2, 3, and 4. Now, look at our target sequence, Y. It contains 2, 3, 4, and 5. Notice anything? The target is literally just the input sequence shifted over by exactly one position. This offset by one concept is the total foundation of next token prediction. It's exactly how the AI learns the structure and the flow of human language.
Moving right along to Section 2, Coding Pairs in Python.
Let's transition from the theory into actual practice, right? Because it's one thing to talk about shifted numbers, but how do we genuinely build this? Building this out in Python involves 3 progressive steps. First, we read the raw text into our program. For our example, we're using Edith Wharton's famous short story, The Verdict. Next, we have to tokenize it. We use a byte pair encoding tokenizer, or BPE, specifically through a library called TickToken. And what's honestly brilliant about BPE is that it breaks down unfamiliar words into smaller subword units. That means it can handle any unknown word you throw at it without crashing or needing some special unknown tag. Finally, once we have our tokens, we slice them into those input and target arrays we just talked about.
So how does this translate into actual high-level Python commands? First, we use tokenizer.encode on our raw text to get our encoded text array. Then, to get our input X, we slice the array from the beginning up to a specific limit, which we call our context size. To get our target Y, we take that exact same slice, and here's the magic. We start one position later, shifting the whole thing by 1. It's incredibly elegant code that perfectly mirrors the math.
All right, Section 3, Understanding context size.
You literally just heard me mention the term context size. So let's formally define what this means and why it matters so much. Context size is basically the AI's field of vision. It is the maximum number of consecutive words or tokens that the model is allowed to look at to predict the next token in the sequence. If the context size is too small, the model totally forgets what the beginning of a paragraph was even about. It essentially dictates the fixed length of the input sequence we feed into the model during training.
Now, for our educational purposes today, and really just to keep the math super simple on screen, we're using a tiny context size of 4. But in the real world, no way. You need way more context to generate coherent text. When you're building your own models, a common starting point for context size is 256 tokens or higher. And honestly, modern massive LLMs can have context sizes in the tens or even hundreds of thousands. That allows them to basically remember entire books at once while predicting the next word. It's wild.
Okay, Section 4, Implementing a data loader. So now that we know how to create a single pair of data, we need a way to feed thousands or millions of these pairs into our AI without our poor computer just bursting into flames. We are shifting from crafting single, artisanal data pairs to building a fully automated industrial pipeline. Enter the data loader. This is a built-in utility in Python, the framework we use to build neural networks. Think of the data loader as our automated conveyor belt. It wraps an iterable around our raw dataset. So instead of us having to manually pull data, keep track of our place, and feed it into the model bit by bit,
The DataLoader automatically fetches the data samples in nice, neat little batches and delivers them right to the AI. To get this conveyor belt running smoothly, we first have to create a custom dataset class in PyTorch, and it requires 3 very specific Python functions. First is under and init, which runs once to set up and initialize our data. Second is under len, which simply tells PyTorch the total number of rows or samples in our dataset. And third is under getItem, which dictates exactly how to fetch a single row of token IDs when the DataLoader asks for it. Once these 3 are set up, the DataLoader basically takes over all the heavy lifting.
Which brings us right into Section 5, Batch Size and Parallel Computing. We've got our conveyor belt running, but right now it's only carrying one single item at a time. Let's talk about how we can build even greater efficiency by processing multiple pieces of data at once. I want you to ponder this question for a second. Why process data in batches instead of just one by one? I mean, if the AI learns by seeing one pair at a time, why complicate things, right? Well, think about grocery shopping. Would you buy one single apple, drive all the way home, and then drive back to the store just for a banana? Of course not. You'd grab a cart and batch your items together to save time.
Batch size is an absolutely crucial hyperparameter, and it comes with a major trade-off. If you use a really small batch size, like 1, your memory usage stays very low, but your model updates become super erratic and noisy because the AI is practically overreacting to every single individual word. But if you use a large batch size, like 8 or much higher, it's going to require way more computer memory. The upside? The learning updates are so much smoother and more stable because the AI is learning from an aggregated average of the data.
To actually support these larger batches, we use something called parallel computing. This just means we're using multiple computer processes simultaneously to fetch the data. See, in Python, there's this bottleneck called the global interpreter lock, and it can really slow down data loading. But by adjusting a simple setting in our PyTorch DataLoader called num.workers, workers, we can spin up multiple independent worker processes to fetch data much faster. It completely bypasses those limits, ensuring our AI never has to sit around waiting for its next batch of data.
And finally, Section 6, Stride and Batch Effects.
So, we have our data, our context size, and our batches. But how exactly do we navigate through the entire text document systematically without accidentally missing information or, worse, unfairly repeating things? To really grasp this, I want you to think of a moving picture frame sliding across a comic strip. That frame is your context size. You can only see a set number of panels at any one time. Once you look at those panels, you have to physically slide the frame to the right to see what happens next in the story. The big question is, exactly how far to the right do you slide that frame for your next batch?
That sliding motion, we formally call that stride. Stride is literally the exact number of positions the input window shifts across the text to create the very next batch of data. It basically dictates the rhythm of our sliding window approach as it moves across our entire dataset.
And comparing these 2 examples brilliantly illustrates why stride matters so much. If we set our stride to 1, the window only shifts by a single position. This creates massive overlapping redundancy in our data batches. While it is thorough, too much overlap can actually cause our model to overfit, basically memorizing the text rather than actually learning from it. On the flip side, if we set our stride to 4, which happens to equal our context size in this example, the window jumps completely past the data it just saw. There is 0 overlap, allowing us to fully utilize the dataset efficiently without overexposing the AI to the exact same sequences over and over again.
All right, let's do a super quick recap of the incredible journey we just took from raw text to model ingestion. We established that LLMs learn by next token prediction. We slice raw text into offset input target pairs using a BPE tokenizer. We rely on context size to dictate exactly how much the model sees at once. We built a data loader to act as our automated conveyor belt for batches. We learned that batch size is this really delicate balance between computer memory and training noise. And finally, that stride controls our sliding windows overlap to help prevent overfitting.
So we've completely built the assembly line. Our data is batched, is sliding perfectly, and it's ready to go. But right now, they are literally just raw numbers. How on earth do we turn these raw numbers into deeper mathematical meanings that the model can actually understand and associate with complex concepts? Well, that requires turning our tokens into something called embeddings. And that is exactly what we will tackle next time. Until then, like, share, subscribe to Yurix AI for a new lecture every day. Hit the bell.